Hello everybody, myself Jyoti and this is second lecture of transient response of circuits. Today we are going to study about series LR circuit where we will study about the growth of current in LR circuit and decay of current in LR circuit. So first we will take growth of current in the LR circuit. A source of EMF E is connected across a series combination of L and R. We have L and R as in the series combination. We have applied a battery or a source of EMF, you can say, and there is a switch S. The current I flows like this. Okay. Now, initially the current in the circuit is 0, and when the switch S is closed, current will start flowing in the circuit, and the EMF equation for the circuit is given by E equals to L di by dt plus I into R, because E, it is the total EMF of the battery. This E, it is equals to voltage across L, that is L di by dt, voltage across R, that is I into R. So that is how we are getting E equals to L di by dt plus IR. So what we can do is we can shift this IR over LHS. So we will get L di by dt equals to E minus IR. Then I divided by L throughout the equation. So I will get di by dt equals to E by L minus IR upon L. And in the next step, I have taken minus R upon N common. So here I will get I and minus E upon L. I have taken R upon L common. So I will have to divide by R. So I will get E by R. So that is how I get minus R upon L, I minus E upon R. Now di, I shifted this bracket to the denominator on the LHS. So di upon I minus E upon R, it is equals to, I shifted this dt to this side. So I get minus R upon L into dt. Now we can see the variables are separate. On LHS we have all the terms of I, and on RHS we have terms of T. So we can integrate and we will get integration of di by I. It is log I. So similarly, integration of di upon I minus E by R, it will be integration log of I minus E upon R. It is equals to minus R upon N as it is integration of dt, that is T. So we will get this plus C. So we know that C is a constant of integration, and for finding out constant of integration we will have to substitute initial conditions. So at t equals to 0 we have current equals to 0. So we will substitute this value. So we will get log of I is 0. So I will get log of minus E upon R. This t is 0. So this term will become 0 equals to C. So basically I am getting C equals to log of minus E upon R. So if I will substitute this value of C in equation 1, I will get log of I minus E upon R minus R upon L into T plus log of minus E upon R. Now I shifted this term to R LHS. I will get log of I minus E upon R minus log E upon R equals to minus R upon L into T. Log A minus log B, that is log A upon B. So that is how I will get this term. And then taking anti-log of both sides. So anti-log of log, that is I will get just this term I minus E upon R upon minus E upon R, and anti-log of this term will be E raised to minus R upon L into T. So I am getting this. Then I will cross multiply with this minus E upon R to this side. So I will get I minus E upon R equals to minus E upon R, E raised to minus R upon L into T. I shifted this term over here. I got this term, and then I have taken E upon R common. So I will get 1 minus E raised to minus R upon L into T. Where E upon R, it is the maximum current which will be flowing through the circuit, because capital E, it is the maximum voltage. So E upon R gives the Im, that is the maximum current. So I, it is equals to Im 1 minus E raised to minus R upon L into T. Now this term L upon R has dimensions of time and is called as time constant of LR circuit. It is written as tau, and suppose I write like this, I equals to Im 1 minus E raised to minus T upon tau, where we have Im equals to E upon R and tau equals to L by R. You have to remember this and this because this is very important for solving problems. When T equals to tau, when at t equals to tau, in the sense when it is equals to time constant, we will get I equals to Im 1 minus E raised to minus T by T. So that will become E raised to minus 1, We know the value of E is 2.718. So if we substitute that and calculate, we will get I equals to 0.63 Im. So if you try to define time constant basically it is the time required for the current to reach 63% of its maximum value. So this is how we define time constant for a circuit where for a LR circuit where there is a growth of current. There is another way of defining time constant that I will tell you later. Now let us take, now this was everything related to growth of current. Now we will talk about the decay of current. Now suppose the steady state is reached and the growth of in the growth circuit and a current Im is flowing the circuit, and we switched off the battery, so we will have 0 equals to L di by dt plus IR. Steady state has reached I equals to Im, and after that we switched off, so E will be 0 because we have the equation E equals to L di by dt plus IR. Now E is 0 because we have switched off, so we will get 0 equals to L di by dt plus IR. So I will shift this term over here, so I will get L di by dt equals to minus IR. Then shifting current terms on one side and time terms on another side, I will get di by I equals to minus R upon L into dt. Log di by I, it is nothing but log I equals to minus R upon L into t plus constant of integration. Again, for finding out the value of constant of integration, we will have to substitute initial conditions. So initially at t equals to 0, we have I equals to Im. Remember this boundary condition or initial condition, because during growth circuit at t equals to 0, we have current equals to 0, but during decay the steady state is reached, and after that we are switching off. So at t equals to 0, we have I equals to Im. If we substitute this value, we will get log of Im equals to C, implies C equals to log of Im. And when we will substitute this value back to equation 2, we will get log I equals to minus R upon L into T plus log Im. Shifting this log Im to the LHS, log A minus log B, I will get log A upon B equals to minus R upon L into T. So I will get I upon Im equals to e raised to minus R upon L into T. Shifting Im to the other side, I will get I equals to Im e raised to minus R upon L into T. So if you substitute t equals to tau, you will get, and calculate, if you substitute here t upon tau, you will get Im e raised to minus 1. Value of E is 2.718 raised to minus 1. So you will get I equals to 0.37 Im. So for decay, remember during growth we have defined time constant. So time constant during growth, it is defined as the time required for which the current reaches 63% of its maximum value. Similarly, in a decay circuit, you can define time constant as the time required for the current to decay to 37% of its initial value. This is the current growth curve where steady state value is reached over here, and this is the decay, like this. So here we have plotted the current on the y-axis, time on the x-axis. So it is like this. Okay. Thank you so much.